quick video to go over the topic of oxidation reduction reactions. Right now we're just going to talk about the pieces that are still included in the AP test content for this year. So most of this information would have been in our unit on electrochemistry, which has been cut from the exam, but being able to identify an oxidation reduction reaction and identify the things within it is still an included topic. So that's all we're focusing on in this video today. So the oxidation reduction reactions are commonly called redox reactions because it's easier to say. These are electrochemical reactions. Now the word electrochemical, that means we're dealing with electrons. It's a reaction in which electrons are transferred from one compound to another, or one species to another. Now we know from our previous information that all of our metals tend to lose electrons. And when a species loses electrons, we say that it has been oxidized. Now similarly, we know that a lot of our nonmetals will tend to gain electrons. And when a species gains electrons, we say it's been reduced. Now, I know that particular pairing of terms is super annoying. Everyone thinks it's annoying. Everybody hates this. But we really can't change it because it's been this way for so long. So we kind of just have to hate it, accept it, move on, pretend it's all fine, and it'll mostly be okay, you know? You only carry some residual bitterness with you. It's all good. One important note, this is different from ionization, which does also deal with electrons either being gained or lost. But this one's a bit more broad. It doesn't have to be a single element creating an ion of itself. We can have electrons transferred between species within compounds or other situations. So it is a bit different. So let's take just a very general overview of an electrochemical reaction. In such a reaction, we have some atom X that loses some number of its electrons and some atom Y that gains those electrons. This is the basic idea behind all electrochemical reactions. And so like we said on the last slide, this element X, this is losing electrons. So this atom is being oxidized. This atom Y, this is gaining electrons. This atom is being reduced. Now you might have noticed these terms down here are opposite. We can sort of term these in either direction. So this atom is losing electrons, so it is being oxidized by Y. Y is the oxidizing agent. Y is causing X to be oxidized. Y is oxidizing X. Now we also know that Y is being reduced. It's gaining electrons, it's being reduced. So X is reducing Y. It's causing Y to be reduced. So we could also call it a reducing agent. We're going to talk through several examples of these because it is really easy to get these terms sort of flip-flopped and backwards. The important thing to start off with is being able to remember what goes with what. Oxidation and reduction. Which one is gaining the electrons? Which one is losing? And so there are two memory devices, at least that I've heard of, so I'll show you both of those. The first is Leo the Lion Says Grr. So this stands for Leo, losing electrons is oxidation, lose electron, oxidation. He says grr, gaining electrons is reduction, gain, electron, reduction. Again, this is just a way to keep these terms straight, remembering that oxidation, that's losing electrons. Reduction, that's gaining electrons. The other one is oil rig, which says oxidation is loss, reduction is gain. Again, same thing, just finding a way to remember these terms and keep them straight, because that really is the hardest part. It's easy for us to look and see where the electrons is moving. it's harder to keep it straight which term goes to which effect. So, redox reactions. When we talk about these, when we are trying to figure out what's being reduced and what's being oxidized, what we really want to look at is the oxidation number. And there are 5 rules to figuring out what the oxidation number of a species is, and we'll get to those. We'll look at how to determine an oxidation number. But right now, the 2 big rules are that when an atom is losing electrons, its oxidation number increases. And so losing electrons, that was oxidation. So if the oxidation number goes up, that is the atom being oxidized. When an atom is gaining electrons, its oxidation number decreases. Gaining electrons was reduction. So if oxidation number decreases, that atom is being reduced. Now we can kind of see why this term was picked. We can get a little bit of justification for it, right? If the oxidation number goes down, we've got reduction. If the oxidation number is reduced, reduction. Okay, now that kind of makes sense. The other way you can think about it is that if an atom is gaining electrons, its overall charge is decreasing, and so its overall charge is being reduced. So a little bit of justification for it there. It'll probably still be a bit frustrating, but that's a bit of the reasoning behind the word choice. So let's look at this example. Here I have given you the oxidation numbers for each species in this redox reaction. Like I said, on the next slide we'll talk about how to figure these out for ourselves, but right now I've given them to you because we just want to look at this effect. So we're going to look at the oxidation number going from the reactant side to the product side for each species. So looking at zinc. On the reactant side, it has an oxidation number of 0. On the product side, it has an oxidation number of positive 2. Its oxidation number is increasing. Therefore, it is being oxidized. Looking at hydrogen, on the reactant side, it's got an oxidation number of positive 1. On the product side, it's got an oxidation number of 0. Its oxidation number decreases, so it's being reduced. Now again, we could just look at what's going on with the electrons here. We can see that for zinc to go from a neutral atom to a +2 ion, it must have lost electrons. And as we know, losing electrons is oxidation. So again, we've got this being our oxidized substance. And we know that for H to go from a positive ion to a neutral molecule, it must have gained electrons, and we know that gaining electrons is reduction, so we could have figured it out that way. But in general, I think being able to look at the oxidation numbers is a bit easier to keep straight. So these oxidation numbers, they're not quite the same as ionization numbers. They do tend to be similar, but we can't rely on that to always be the case, because an atom can have more than one oxidation number. It typically only has one ionization state, but it could have more than one oxidation state. So we're going to go over 5 quick general rules to determine our oxidation number. Rule number 1 says the sum of the oxidation numbers must be the same as the ionization number of the whole molecule, which is typically 0, but if we've got an ion, it can be different. The ionization number on the whole molecule, that's just the charge on the molecule. So just like before, just like back in Unit 1 where we talked about building compounds, we're still looking at the overall charge here and making sure everything within it adds to that charge. Nothing new here. So to give you 2 examples, this compound we know has an overall charge of 0. It's a neutral compound because there's no charge here. So the oxidation numbers of everything, each species in it, must add to 0. By contrast, the hydronium ion pictured here has an overall charge of +1. So if we added up the oxidation numbers of both species in here, they would have to add to 1. So nothing new here, right? We've had this rule all year. The oxidation numbers of each species in a compound is going to add to the overall charge. Rule 2, an ion's oxidation number will be the same as its ionization number. So if we have an ion with a charge on it, its oxidation number just equals that charge. So for example, all the halogens will have an oxidation number of -1. That's the ion charge they would have. Cations by themselves, for all of the group 1, column 1 alkali metals, they're all going to have an oxidation number of +1. All the alkali earth metals, they're going to have an oxidation number of +2. These are the charges they'd have as ions. It's also their oxidation number. All right, now for the good ones. Hydrogen is usually +1. Usually. There are exceptions, but you know what? We don't need to worry about them right now. We'll just pretend that doesn't exist. Oxygen is usually -2. Again, we'll just sort of gloss right over this mention of exceptions here and figure that's something we can worry about later. Diatomic molecules have an oxidation number of 0, right? They have no charge. If you think about the hydrogen molecule H2, it's able to perfectly share the electrons with itself because both hydrogens have the same electronegativity, they're pulling with the same strength. There's no uneven electron distribution or charge density anywhere. There's no charge on that molecule. It's got an oxidation number of 0. So now hopefully we could see how we got these numbers on this equation. So zinc, being a pure single element with no charge, would have a number of 0. We have a hydrogen ion here. Its oxidation number would be equal to its charge plus its hydrogen, which tends to be +1. We've got a zinc ion here with a charge of +2. This is a cation, and so its oxidation number is the same as that charge, +2. And finally, hydrogen gas, a diatomic molecule, has an oxidation number of 0. And so just like we've been saying, a species is oxidized when it loses electrons. Here we see that it is the zinc that must be losing electrons because it goes from neutral to charged. And we see that its oxidation number increases. The species is reduced when it gains electrons. That'd be the hydrogen here. The hydrogen goes from an ion to the diatomic molecule. It needed to gain electrons to do that. In addition, its oxidation number is reduced. It goes down. Now, remember what I said about going about it the other way, naming the other way. Whatever species is reduced is also acting as the oxidizing agent. So we know that H is being reduced, but as it does so, it's also oxidizing zinc. It's causing zinc to be oxidized because it takes the electrons away from it. So we could also refer to the hydrogen as the oxidizing agent. Same thing with our zinc. Zinc is oxidized, but it's also the reducing agent. Zinc is reducing hydrogen by giving it electrons. It's giving it extra negative charges. It's causing its oxidation number to be reduced. Let's go through one example for practice. So here we've got a chemical reaction, we've got a redox reaction, and we want to identify what species is being oxidized and what species is being reduced. So the first thing we need to do is write the oxidation number for each species, and I'm just going to put it on top of each species here in this equation. And so this will be, again, just like the very beginning of the year. We said that oxygen is always -2 for its oxidation number. So we'll put in all of our -2's, and then let's take a look at this compound first. If oxygen's -2, and the whole compound needs to add to 0 because it has no charge overall, then our iron has to be +3. If oxygen's -2 Negative 2 times 3 is negative 6. We need a total of 6 positive charges over here. This one has to be positive 3, so that we've got 3 times 2 for positive 6, negative 6, and overall sum of 0. And the rest are going to go about in that same manner. We know oxygen's negative 2, this carbon must be positive 2. We've got a pure element here, no charge. It's got an oxidation number of 0. And again, oxygen's negative 2. We've got 2 of them, so we need a total of 4 positive charges from this carbon. And I've color-coded these so that the red numbers go with the iron, the blue go with the carbon, and the oxygen oxidation number is black because it's not changing. It's neither being reduced or oxidized here. Alright, and now let's figure out which is which. So we'll look at iron. It starts with an oxidation number of positive 3. Afterwards, it has an oxidation number of 0. So its oxidation number is decreasing. In other words, it's being reduced. Our iron here is being reduced. It's gaining electrons. Its oxidation number decreases. The carbon is being oxidized. It goes from positive 2 to positive 4. Its oxidation number is increasing, so it is being oxidized. It is losing electrons. All right. So hopefully that made sense and is enough to pick redox reactions out of a group of reactions. Again, that's really the main part of this topic that could still appear on this test, is just recognizing here, being able to put in the oxidation numbers to recognize that oxidation and reduction are happening, and then being able to pick out which piece is being reduced and which piece is being oxidized. So you can take a look at more examples of those if you want, and let me know if you have any questions.